Hi class, we are moving on to chapter 9.4, Similarity. This is the last section of chapter 9 before we move on to chapter 10. We're going to talk about similarity. So similarity has a lot to do with transformations, isomorphisms, and isomorphic spaces. More so with the transformations. An isomorphism we know is two vector spaces that are basically the same. Here, the only similarity to that is that we're talking about two matrices that are basically the same. So matrices basically that have certain characteristics in common and how to find those, and how they relate to transformations. Okay, so let's get started. So I think that, as I said in the last video, it's very important that you're familiar with the section 9.3 and also very familiar with the change of basis information from chapter 4.4. So if you're a little fuzzy on those, I suggest that you just review them one more time before you watch this video. 9.3, we really only had like three really important things, and that was the representation of a vector as a coordinate vector, and then how to go from a coordinate vector to the actual representation of that vector, what that vector actually looks like. And then the order that we need to make our transformation. So that stuff's going to pop back up, and we're going to look at it under the guise of change of basis as well. Okay, so let's go ahead and get started. So again, review chapter 4.4 if you have not already. Also review the last section, 9.3, if you're still fuzzy on that a little bit. It'll be worth it to get through this video. So again, for this section, we're going to focus on the special case where our linear transformation is from a vector space V onto itself. So the last section, we looked at from a vector space to perhaps, or more so, a different vector space. Here we're going to go from V to itself, right? So here we're staying within a single space. We're not diverging to a secondary space W. Right, so our transformation goes from V to V. Say that G is a basis for V. Okay, and then let's say that we have H, which is a secondary basis for V. Right, so both of these are different bases for V. So there's going to exist a transformation matrix that we'll call A. That is with respect to G, and there's also going to exist a transformation matrix B with respect to the basis H. Okay, so again, A and B both are from V to V, right? It's just that one is represented in this basis, and then the other is a representation under this basis. H in this case might be simpler to work with than the basis that we're given G. Okay, that's our assumption for right now. So note that we can change from one basis to another, but we use the same basis for our domain and codomain since T maps a vector from V to V. Okay, so we can either look at this transformation in terms of G to G or in terms of H to H, right? So here we'll say the transformation, the image of X under the basis of G is the same as the transformation by A, which is the transformation with respect to G, times our vector represented in the vector G. Or if we're talking about B, it'll be the same thing, but under the representation of H. Okay, so example. Let's say we have G be the standard basis, E1, E2, or 1, 0, 0, 1. And H is the basis 1, 1, and 1, 2. Right? Let A be the transformation matrix with respect to G, right, of 1, 1, negative 2, 4. So this is a transformation in terms of the basis G. So if we want to find the transformation matrix that is with respect to H, we can. We have pretty much all the pieces except for the transformation with respect to H. So what we're going to do is, just like we started off with the last video, right, is we are going to transform each of the bases in H by this transformation A. So what that's going to do is basically, since A is a transformation with respect to G, this transformation is basically going to have us be some coordinate vector in G. So what we need to do then is we need to represent our transformation that's now in G back into H. So we're taking our basis vectors, we're transforming them, and we're turning them into something that is now in the representation of G, and we got to change that back to the representation of H, so that now we have the transformation column vector 1 and 2 being transformed and then represented in H, so that we have the transformation of B. Okay, so you might say, what the heck did you just say, Professor Williams? Let's just work through this problem and you'll see what's going on here, right? So we're going to transform each basis vector of H by A, okay, and then we're going to find that coordinate vector, right? That's a coordinate vector in G in terms of H. So normally what we would do is we would first take this H and represent it in G, so it looks like X in terms of G, transform it in terms of, or by A, and then we'll have this coordinate vector in terms of G. We take that coordinate vector in terms of G and we represent it in terms of H, and now we have our first vector in terms of H. So the difference here is that G is the elementary standard basis, right? So we don't have to change this into terms of G because this representation is going to be the exact same as it is now because G is the standard basis, right? So we're going to take T of H1 and we're going to transform it. Okay, that's going to give us 2, 2, which if you notice, right, remember this is this right here is H1. It just gives me 2H1. Okay, so the image of T in terms of H I need to find. Okay, so in reality this transformation here is really represented in terms of G, right? It's just that G is the standard basis, so it doesn't matter if I put it on there or not for right now. But we're going to solve this in terms of H, so we get the coordinate vector of this transformation in terms of H, which is 2, 0, right? So if we turn this into two equations and we solve this system, we're going to get A and B is 2 and 0, which makes sense because what happened when we transform this? We got 2 times our H1, right? 2, 0, 2 times the first one. Right? So note that the transform of H1 is 2H1 plus 0H2, which is 2H1, which is what we got from our transformation. Okay, 2H2 is the same thing. We have our transformation by A times the second basis vector of H. It gives us 3, 6, which if you notice is 3 times my H2. Okay, so note that T of H2 in terms of H, I now have to set up this equation again. Okay, so I take the inverse of this matrix and multiply it by my resultant vector so that I can get my scalars. I get 0, 3, which is matches with what we had here for the transformation. Okay, really this is working so well because our first basis is the standard basis, so I'm not having to represent these H1s in terms of G first and then taking the transformation. So that's why we're getting this neat result. So our transformation matrix B with respect to H is this, right? I'm putting my two results, right? The transformation of H1 in terms of H, and then the transformation of H2 with respect to H together. That gives me a diagonal matrix. Okay, a diagonal matrix, this B, is way easier to work with than this matrix A that I have. Okay, if I had to do transformations with this, it's way easier to transform a vector based on this transformation matrix than it is on this transformation matrix. Right, so our B matrix, our basis of H, may be easier to work with than it is for our G basis. Okay, so now let's take an example. All right, let's start with a vector. Let's say V is the vector -1, 4. Hopefully you guys remember that diagram that I referenced in chapter 9.3 a lot. But we take a vector, we represent it in terms of the basis of the space that we're in. So in this case, I'm going to find V of G, or V in with respect to G, the coordinate vector. Then I transform it by the appropriate transformation matrix. I will then be in my codomain, which in this case is still V. And then I can use that vector representation, that coordinate vector representation, and then turn it back into its original vector for the transformation, right? So that little U that we had from the diagram in 9.3. So that's pretty much what we're going to do here, okay? So V is -1, 4. If I want to compute the image of V, I can do it two different ways, okay? First, I can find the coordinate vector representation with respect to G. Since G is the standard basis, it's not going to change the way the V looks, right? So to represent it in the standard basis, it's already in the standard basis, so that's convenient. To find the image of this, I do what I was doing before, right? So for an image with respect to G, I multiply it times the transformation matrix with respect to G. Okay. So I'm going to multiply A times V of G. So this was my A, this is my V of G, and then I'm going to get my vector with respect to G. And then now that this is in terms of G, this is a coordinate vector, so I need to multiply these times the bases of G to get the original image of V. But as we said before, G is the standard basis, so this is the image of V under that transformation, right? So if I get this and I multiply it out, I'm going to get the exact same thing because I have the standard basis E1 and E2. So that's nice, right? Whenever we're in the standard basis, it's easy because it's what we're used to, right? So that's what my image, my vector looks like under this transformation of G. Okay, so here A is a little bit, it's not complicated, but compared to the transformation matrix B, it is, right? But it's, I know we just plug this into the calculator, do it by hand, it's not too difficult, but it could be if there was a bunch of fractions in here, right? So if I want to do this the other way, that's way one, right? The second way is to do this all in terms of H, okay? So I find V in terms of H, so I set up my equation so that I can represent this under the basis of H, right? So A times 1, 1 plus B times 1, 2 will give me my V out. So I need to find A and B so that I have the coordinate vector representation of V with respect to H. So, you know, it's just an equation for me to solve. You can do RREF, you can use inverses, whatever is necessary. But that'll give me -6, 5. So the vector, the coordinate vector representation of V with respect to H is -6, 5. Okay. If I want to see what this looks like after it's been transformed with respect to H, okay, then I need to multiply this times my transformation matrix B, because B is the transformation matrix with respect to H, the basis that I'm working in right now. That was the 2003. Okay, very easy to figure what this is. -12 and 15, right? That's why we made this in the first place, because it's an easy basis to work with. Transformation to work with. So it just multiplies the first entry by 2 and the second entry by 3. So -12, 15 is the result. And again, this is a coordinate vector. So in order to find my T of V, I need to take this and I need to write it in terms of the basis vectors and add everything together. Okay, so -12 times the first basis vector plus 15 times the second. When I add these across, notice I got -12 plus 15 is 3. -12 plus 30 is 18. Okay, it's the exact same T of V. So we start in the same place. We go into the appropriate basis that we're going to work in. We use the appropriate transformation matrix, and then we take the coordinate vector and we write it in terms of those basis vectors, and we multiply, add everything up and multiply it out to get our T of V. So I did it here in terms of H as well, and I got the exact same thing, right? Which we would expect to do. So note that in order to find b equals 2003, we had to do a couple of things. Okay, so really what we're going to do is we're going to use this previous example here, and we're going to write it out in general. We're going to generalize the process that we did here so we can do this anytime. Okay, so remember what I said. We were using this information here to figure out what b was. So I would take my h basis vector. I need to write it in terms of the basis of the transformation matrix I'm going to use. In this case, I didn't have to because it was a standard basis. I didn't have to do any, I didn't have to write this in terms of a different basis, but that's what I would normally do. If G was not the standard basis, I would have wrote this in terms of whatever the basis G was. And once this is now a vector in terms of G, I can multiply it times the transformation matrix I have, which will give me out the transformation column vector for, you know, the first one or second vector or what have you for B that I'm trying to find. And then I would have to then take this and then rewrite it in terms of H, because I need my transformation matrix, those vectors there, to be written in terms of H so that it can be a transformation matrix with respect to H and not with respect to G. So this is what I would get as a result, and each of those column vectors I would then turn it into representations of H. So that's me explaining what we're going to show now algebraically. Okay, so we are just going to follow what it is that we did in that previous example, right? So our transformation matrix of T with respect to H, which is what B is. So we had to take each basis vector of H and transform it with A. Now, again, in order to do that, I have to write that vector in terms of the basis that that transformation matrix is in, which is G. Okay, so the transformation matrix of T with respect to G, which is what A is. And then we find its corner vector representation with respect to the basis H, because I need B to be a transformation matrix with respect to H. So for each of our column vectors of B, B1, B2 up through Bn, we have the following. I transform my H vector in terms of with respect to T, and then I take that result and I write it in terms of the basis H. Okay, so how do I do that? First, I have to take H sub I, whichever one I'm looking at. I need to turn it into a vector representation in G. Then I can multiply it times that vector representation, or I'm sorry, that transformation matrix in G, and then multiply it by H inverse. Now, what is H inverse? Well, look here, right? Each time I did this, okay, I had some inverse times my resulting vector. Okay, that's what I did here, right? And what is this? This is just the column vectors of H inverse, because when I set this equation up to find its scalar representation, the C1 and C2, or AB in this case, it makes an equation for me, right, which is created by its vector representation, or its basis, its linear combination by using the basis vectors of H. So I'm always going to have H inverse, which is where H is basically made from the basis vectors of H. Okay, so we have a little formula now that we can do. Okay, here, right, where H is those column vectors, are column vectors made from the basis of fancy H here. All right, so we say P is equal to P from H to G. This is the transformation matrix from H to G, and it's given by looking at each H1, H2 up through Hn under the basis representation, the coordinate vector representation in G. So we're going to write each of these vectors under the basis G. Okay, and that matrix that we get from doing that is our transformation matrix from H to G, because we're taking the basis. Remember, every vector is written in terms of a basis, right? And so now we're taking those basis vectors, and if we write them in terms of G, that's going to give us a transformation of anything that we have in H and representing it then in G, because we transform the core components that make up every vector in under H, and we've turned them into now G, right? So doing this gives us a transformation matrix from H to G. Okay? And the inverse of that from G to H is just the inverse of this matrix, which we saw in 9.3, or you can think of it the other way as basically doing the same thing. We take the basis vectors from G and we represent them in H. Okay? That's the easiest way to think about this. If I'm going from H to G, I take the basis vectors of H and I represent them under coordinate vectors of G. If I'm going from G to H, I take the basis vectors of G and I represent them in the basis H. Okay, and once we have one, you can find the other because you should be able to take an inverse. If for some reason it's not square, which in this chapter we'll talk about later in this section, it's always square. That's how we would do this. Okay, so our B here, very similar to this diagonalization, although it's not a diagonalization, it's P inverse AP. So here, A is the transformation matrix in G. P is the change of basis matrix from H to G. P inverse is the change of basis matrix from G to H. Right? So that's how we find the transformation matrix with respect to H. Okay? Very important here that P always represents the change of basis from the basis you want to go into to the one that you want to start off with. So if G represents the basis in what would normally be the domain and H the codomain, that's what P is. You never swap these orders. So I know when we had in 4.4, we considered P to be whatever one we were in that we wanted to go into. It's not the same here. Here, P is always from H to G. P inverse is always G to H. Okay, don't swap the orders or you'll get confused in the things we have to do in this course. Right. So we define P as the change of basis matrix from H to G. Okay. So again, here's that diagram that very similar to what I had in the last video, but slightly different. So here, instead of going from the top down, we're doing the opposite. Here, I need to take my my vector, and I need to represent it in whatever basis I am. I can change it into the new basis that I'm going to by the transformation matrix P. Okay, so here from H to G, so B prime would be the H, the B is the G. B is always the one that we're starting in. B prime is the one that we normally go to. Right, so most textbooks use the B and B prime. We're using H and G. So if B prime is H, right, G is the B. P transforms us from H to G. We use that transformation matrix A that we're given, that's already in terms of G. And then once we get our result, we transform it back into H by the inverse matrix, right? So we go from, take our vector V, we represent it in H, we go from H into G. Now that we're in G, we transform it with A. Our result is now still in G, so we got to bring it back to H, right? Another way of doing that is to just use the transformation matrix B. So here, this A prime is what they're calling the transformation matrix B, right? So slightly different notation. Everything is really the same. So instead of going P, A, P inverse, we could go directly there with B, right? This B, in this case, A prime, if we call this A prime instead, that's exactly what it would do. So P first times A times P inverse does the job of multiplying just straight by B, right? But again, a lot of times we don't know this transformation matrix, which is why we went through all that work to find it before. So now that we know how to find it, we can compute it indirectly because most of the times we cannot compute it directly, okay? So again, very similar to what we're doing in 9.3. take your vector, put it into the representation of what you need, transform it into the basis that your transformation matrix is, do your transformation, then change your basis back into the one that you started off with. Okay. So for our steps here, let's say that we're given a basis G and H and a transformation matrix B with respect to H. So here things are slightly different because normally we were given a basis G, a basis H, and our transformation matrix was A. That took us from G to G, right? It was with respect to H. Here this is for B, from H to H. So we have to do things slightly different, right? If this is H and this is our G, right? We're kind of swapping things around here, right? So we're going to do this in a slightly different order, which is, I feel, is fine, because what we did before was we were in H, we had to transform into G because our transformation matrix was given to us in terms of G, and then we went back into H. So here we're just going to do slightly different. We're going to start off in G, go into H. Since we have B and not A, we're going to change into world of H, and then once we have our result in H, we can change our basis back into G, right? And that's because of what we're given. We're given B here and not an A, right? If we had both, we can just do both. So we're going to be a little bit backwards here in terms of what we've been doing so far, right? So what we're going to do is, since X is in V and G is the basis for V, we know that X in V means that the representation of X with respect to G is still in V because G is our standard basis for V, right? We're going to find P inverse by finding the representation of the basis vectors of G in H, right? Because we're in G right now, we're going to have to move into H to do our computations because our transformation is with respect to H, right? So I need to take my thing that's in G and I need to write it in terms of H, and I can do that by using P inverse. So remember, P inverse is a transformation from G to H. I'm in G already, I need to get into H. So multiplying my vector that's in G by P inverse will put me into H. So now that I'm in H, I can now that I found the transformation matrix, I can change the representation of G by multiplying it by P inverse, right? So I had to find P inverse first, and I had to do that by finding the representation of the basis vectors of G in terms of H. Once I've done that, I can now take that result that I have and I can multiply my vector that's in G so that it is also in H. Now that I'm all in H, I can transform this X of H by multiplying it times B, because B is the transformation with respect to H. Now that I have that, I can change that resultant vector back into G by multiplying it by the change of basis matrix from G to H. From H to G. And then I'm done, right? So most of the time you're not starting off with an X and V. Most of the time you'll be starting off here with X and G with respect to G. So you find your change of basis matrix, you transform your vector, and then you change the basis representation of your vector. Once you change the basis representation of your vector, you transform it, and then once you've transformed it, you change it back. This is what that P inverse AP does for you. Okay, in this case we're going PA P inverse because we have B and we don't have A, so there's a slight moving around of this, right? So example, let's say we have the previous example where our basis for G is the standard basis, H is the 1, 1, 1, 2, okay, and A is this given transformation matrix for me. So notice here, I don't know what B is, okay? So I'm going to do the same thing here, but slightly different because that's how this order goes, right? So this is the transformation matrix with respect to G. I'm going to take something in H, right? Find my change of basis from H to G so that everything is in G because my transform is in G. And then I can then transform my vector and then change the basis back into H. Okay. We already know this information. We've already done all the work here, so we're just going to go over it under this guise instead, right? So my transformation from H to G is given by 1, 1, 1, 2, and that makes sense because this is the standard basis, right? So I didn't really have to transform anything. But let's say we didn't know that. Let's say this was a different basis. What does this look like for us? Well, again, we're going to write this vector in terms of this basis, and we're going to write this vector in terms of this basis. Obviously, without transforming, we're just going to change the basis representation, right? So A times E1 plus B times B2 equaling 1, 1 is just 1 and 1, right? Which is what H1 looks like under the representation of G. Same thing for the second one. We get 1, 2. So again, since E1 and E2 are standard basis, it just looks like itself. Okay. So note also that if we had swapped this around, if I want to look at what G1 looks like under the basis of H, I can. I get 2 and negative 1. Okay. And if I want to look at what G2 looks like under its basis representation of H, then this is what H2 looks like, right? So my inverse is 2, negative 1 and negative 1, 1, right? So here I did exactly what I did here to find P inverse. If I were to have computed P inverse directly from P, I would have got the same thing, right? Because what do you get here? You swap this, so this is 1 and 2. This becomes positive. The determinant is 2 minus 1, right? Or 2 minus 1, which is just 1. So if you swap this around, this is 1, 2, and negative 1, and this changes signs. That's exactly what we had for P, right? So I'm going to take my V, right? I want to represent it in G, right? So again, from what I have, okay, I need to represent it in G, and then once I represent it in G, I can transform it in G, and then I can bring it back into the world of H, right? So this is VG. If I want to find what V of H is, I multiply my resultant vector by P inverse, okay, because that's the transformation matrix from G to H, right? From G to H is V of G. So if I actually do this, right, P inverse times that, I get negative 6, 5, which is what I had in the beginning, right? I called it W in terms of H, but it's the same thing. My vector in terms of the secondary basis was negative 6, 5. I know that B is P inverse AP, so if I were to multiply those things out, I got 2, 0, 0, 3, which is what I found when I did this the slow way, right? The transformation of V with respect to H is the same thing as B times V of H. And if I break B down to P inverse AP, then this is what I get, okay? So here I'm writing P inverse and P in terms of what they represent. So remember, P is from H to G, P inverse is from G to H, right? So if I multiply these two, okay, I'm getting my coordinate representation in terms of G, because this change of basis, all it does is change the basis from H into G. So that's what this under brace is. It's saying that if I take this and I multiply it by the change of basis, I'm going to change the basis. Okay, so then I have P from G to H, and then my result here being transformed by A, and we already know what this looks like. When I take A times V of G, I get the image of V under the transformation in the basis G. And we got that all the way from the very, very beginning, right? A times the representation of X and G will give me the image of that vector in terms of G, right? So that's just that equality that I'm having here. So B times my vector in H. I can break B down into P inverse AP. Well, P inverse AP I know is two change of basis matrices. One from G to H, one from H to G. I know when I multiply these things together, all it's doing is changing the vector representation of V from H to G. So I'm getting out V of G. So that result, A times V of G here, times this change of basis, well, I know that this is the same as that. So now I just have the image of V under the transform of A, which gives me the image of V under the transformation being represented by the basis G. Okay. So now when I multiply this out, this is going to take me from G into H because I'm multiplying it by the change of basis matrix from G to H. So this is going to get me out exactly what I wanted here. So if I want to find the change of the image of V, the transformation of V under the basis of H, I can multiply by B. I can, right, this is just me verifying all that work that I did. Okay. So therefore T of V of H in this case is my change of basis, my transformation A, my other change of basis, and my vector V in terms of H. And so what I did up here, I'm basically going to do again here, just for posterity so you can see what it is that I'm doing. So again, this first thing here, all that does, okay, that first set of multiplication here is going to take this V of H that I have, negative 6.5, and it's going to turn it into the representation in G. Okay, multiplying these two first, we'll take my V of H. These two will turn it into V of G. Okay, so now when I multiply this times A, I'm now transforming, doing transformation in G. Okay, and this should look familiar to you as well, right? We know that this is true. And so now when I multiply it times the change of basis matrix from G to H, I'm taking this result that's in G and I'm going to put it into terms of H, which is negative 1215, which is also what we had from the very beginning. If we, again, want to go all the way to the beginning. Here, I went too far. Okay. T of V of G, we knew was 318. T of V of H was negative 1215. Everything matches up with what we just did here. Okay, here we go. All right. So maybe you want to review that once or twice because I didn't go over it 100 times like I normally did, but that's the way that things work. Okay. So again, 9.3 will make this 9.4 make a lot more sense. So now let's kind of just extend our idea of what similarity is and talk about that a bit more, right? So our definition now is that a square matrix A is similar to matrix B if there exists an invertible matrix P such that A equals P inverse BP, right? So we've seen this already. The change from B to A is called a similarity transformation. Right? So note, if there exists a matrix S such that S times A is the same as B times S, then we start to move some stuff around. We get A is S inverse BS. And if I want to solve for B, I get SA S inverse. Okay. Then A and B are similar. So I used this relationship earlier without showing it to you, but we did this, right? So I gave you this, right? I said that this was B and this was A, and then we moved some stuff around and I said that this was B and that this was A. That's when the things here probably seemed a little bit backwards, right? Because here I'm saying that this is what B is, and then here we were doing things slightly in the opposite direction because I had P inverse first as the first multiplication and P was the last multiplication. And then we went to this example and then I was doing P as the first multiplication and P inverse as the second multiplication. It really just depends on which space you're going from, right? am I given B, then my secondary transformation I'm trying to find is going to look like this. If I'm given A, then that secondary transformation I'm trying to find is going to look like that, right? So it really just depends. You need to be flexible and able to go back and forth. So I hope that didn't confuse you guys as I was going through it, but it's really a flexible sort of situation, right? So here, if A and B are similar matrices, then A and B will have the same determinant. Invertibility, so if one's invertible, then the other one is invertible as well. Their rank will be the same. Their nullity will be the same. They'll have the same trace. They'll have the same characteristic polynomial, the same eigenvalues, including the multiplicities, and the same eigenspace dimension for those corresponding eigenvalues. So in essence, A and B are basically the same. They're not the same though, but they are similar. Now, you can use these things to show that two matrices are not similar. You cannot use these things to show that they are similar. Okay? If you want to prove that something is similar, you want to use this. Find a matrix S that satisfies one of these equations, and then you're fine. Okay? However, if you want to show that something is not similar, you can find the determinant of one and find the determinant of the other and show that they're not equal, so they're not similar. You cannot say, hey, determinant of A equals determinant of B, so they are similar. That's not enough. You could show all of these things are the same, and I would be okay with that. But that's a lot of work. Okay, so the easier thing to do is to use this stuff here to show that two matrices are not similar. Use this definition here to show that two things are similar. Okay, so again, the big takeaways here are follow these steps. Okay, all right. This first step is kind of arbitrary because they're never really going to give you just an X and V and say now you got to represent it in G. In fact, most of the time they're not even going to give you a vector at all. They're just going to say, hey, here's a basis, here's a basis. Now find your transformation. Okay. So it's a lot easier than I outlined here. So if this was semi-confusing to you, it's okay. I gave you more information than you need. Okay. This will help a lot. Just follow the P inverse, right, in order to find your B matrix, right, or A matrix, whatever it is that you need. But really finding these P, just find P, then find P inverse, and the rest of this is pretty easy as a section. Okay, so hope that helps. I hope it's not too confusing for you guys. I know that this is a little thick, these last two sections. I will see you in chapter 10.